All right, good morning. Today is the last lecture for this course. Um, the final exam is next week. It's on Wednesday, the 3rd of May. The time is from 9 o'clock in the morning until 12, so you will have 3 hours to work on the final exam. There will be 5 questions in the exam. The material that will be in the exam will start from Fourier transforms until the content in this lecture. Okay, so beyond that will not be in the exam. Um, you can bring in an A4 paper. You can write on both sides of the paper with a real ink with your own handwriting. Uh, you might have to write down the properties of Fourier transforms as well as some other properties that you may think useful. You may have to write down some of the Fourier transform pairs that you may think useful on the paper. Okay, it's your responsibility, it's your job to do that. Um, you can also bring in a calculator, which is a simple calculator that you have been given from the university, and those calculators are fine. You cannot bring in any communication devices into the exam, or if you do, you have to turn them off. You cannot bring in an advanced calculator. For example, you cannot bring in a computer, a mini computer into the exam. That would be unfair to your friends. Um, yeah, so that would be the final exam, which will happen next week on Wednesday in the morning. And the room for the exam is 201, this building on the second floor, which I believe is the same room as when you did the midterm exam, the same room downstairs, 2 floors down. Okay, so that was about the exam. Now, uh, we last time we were we were beginning chapter 8, which is the discrete time linear time invariant systems. So last time we talked about discrete time LTI systems. It was about DT-LTI systems. Now, when we talk about any LTI systems, the tool that we use is called the impulse response of the system. Okay, for LTI systems, okay, we use what is called the impulse response to analyze the system. Okay, in the continuous time systems, the impulse response is written as h of t. So this is for continuous time systems. Now, for discrete time systems, the notation that we use for the impulse response is h. Okay, the same h. So we will use h, the little h, as the impulse response. Now, what follows x depends on the type of the system we're looking at. If it's a continuous time, then it would be a curl parenthesis t, where t represents the continuous time. If it's a discrete time, then we're going to use brackets here, and inside bracket is the integer n, which represents the sequence number of that sample. So this is the impulse response of discrete time LTI system. So in this chapter, since in this chapter we're talking about discrete time, so the form of the impulse response we'll be using is this form, which is h bracket n. So we'll be using this form in this chapter. All right. Now, once we know the impulse response of an LTI system, so discrete time LTI system with impulse response h of n, and if x is the input to this system, of course, it's a discrete time signal input. And when we measure the output, we denote the output by yn. So yn is the output from the system with impulse response hn with the input signal xn. Then it turns out that we can determine the zero state response y, which is y zero state of n, and y zero state can be determined using convolution sum between x and h. So x hn and star xn. So whenever we write this down, we will mean that this is called the convolution sum. Between xn and xn. Okay, this represents the convolution sum between x and h and x. Now, the operation, the convolution sum operation is actually summation that goes from k equal negative infinity to infinity h of k and x of n minus k. So this is a rather complicated sum, but I will show you shortly how to do this sum given h and x. So before we end, last time we talked about some of the important properties of convolution sums. Some important properties of convolution sum. Okay. First is it is commutative. Okay, commutative. Commutative means that you can switch the order between h and x. It doesn't matter which one goes first. When I write this down, I put h at first in front of x. So h goes here and x goes here. But it turns out that it doesn't matter. I can put x in front of h. I can switch these two, okay, and the result will still be the same. So commutativity says that h of n convolved with x of n is equal to x of n convolved with h of n. Okay, that's commutative. The second property is called associative. Associative says that if I do the convolution sum between three discrete time signals, xn, yn, and zn, okay, I cannot do all three at the same time because convolution sum operation involves only two signals. It is a binary operation. So we have to do two at a time. Okay, we cannot do three at the same time. So we have to pick which pair to go first. Okay, it turns out that um, I can put parentheses here. Okay, so that y and z go first, and then the result from the convolution sum between y and z will be convolved with x, and the result will be equal, just as equal to I put x and y to go first, and then the result convolved with z. Okay, so associativity basically says that it doesn't matter which pair to go first. All right, when you perform three convolution sum between three signals, the order doesn't matter. The third property is called the distributive property. The distributive property says that if I do this, xn convolved with alpha h1n plus beta h2n, where alpha and beta are constants. Now, I can bring x as well as the convolution operation inside the parentheses, just as I would do for multiplication. Okay, and the result will be the same. So this is equal to alpha xn convolved with h1n plus beta xn convolved with h2n. Okay, and even though I'm writing down only two terms in the parentheses, but in reality, there can be more than two terms here. There can be 3, 4, 5, or even infinite number of terms inside the parentheses. And you can do this distribution over all of them. Okay, so those are very basic and important properties of convolution sum. Now, today I'd like to give you a couple of examples of how to do convolution sums, as well as how to find uh, go on, an impulse response from a difference equation. Okay, so let's do an example. Uh, a discrete time RTI system is defined by the following difference equation. So that equation in focus is yn equal to a yn minus 1 plus xn. Okay, where xn is the input signal and yn is output signal, and a is a constant. A is a constant, doesn't depend on n. Now I'd like to find the impulse response of this system. Okay, this equation tells us the relation between the output and the input. So basically it says that the present value of the output can be determined from the previous value of the output multiplied by A plus the present value of the input. So that's how you determine the present value of the output from this system. Now, we'd like to find the impulse response. Hn of this system. Now it turns out that for this system, okay, this is a very simple system. So to find the impulse response is pretty easy and straightforward. If the difference equation is more complex, then this is a rather simple difference equation. But if the difference equation is more complex, then we will not be able to use this method. But we may have to use Z transforms to find the impulse response. But unfortunately, we won't be able to cover Z transforms in this course because we don't have enough time. But usually Z transforms covered in this course, but not in this semester because there's no time. Just I'd just like to point out that if the difference equation is more complex than this, then we might have to use Z transforms. So since the difference equation here is not so complex, we're gonna go ahead and find the impulse response in a very straightforward manner. Now, before we want to find the impulse response, we have to ask yourself what really is an impulse response. So the impulse response is actually the value of the input when the input is the unit sample. So this is what an impulse response really is. But this is not enough. It is not enough just to write this down as an impulse response. But there is one more condition that you have to be aware of when you want to find the impulse response, and that is the initial conditions of all of the initial conditions of the system have to be zero. So no initial conditions. Okay, you must not have initial conditions when you want to find the impulse response. So with this in mind, let's write down the output value at time zero. Okay, so no initial conditions. What does it mean? No IC. Without initial conditions, it means that y minus 1 is equal to y at minus 2 is equal to y at minus 3, and so on, equal to 0. So this is what it really is, no initial conditions. We are assuming that the input is applied at time 0. Okay, we are assuming that the input is applied at n equal to 0. Assuming input applied at n equal to 0. So the prior values of the output before n equal to 0 are all initial conditions. Now, at n equal to 0, okay, y0 from the difference equation, when we plug in n equal to 0, we're going to have y at 0, right? And that has to be equal to a, y at minus 1. Okay, because when n is equal to 0, then the value here would be minus 1 plus x. But we're talking about the unit sample here because we're talking about the impulse response, right? So we need to plug in the unit sample as the input x. So we need to write down the unit sample here, okay, as the input. Okay, right? But because of the 0 initial condition, y at minus 1 must be 0. So I can cross this out and give it a 0 value. And n here would be 0, okay? And we know that the unit sample at time 0 is 1. And this is 1. So when you add them up, you're going to get y at time 0 to be 1. Okay? Now at n equal to 1, y at 1 is a times y at 0 plus delta at 1. Right? I plug in n equal to 1 here. Now y at 0, we can look here and we see that y is 0, it is 1, right? So this is 1. This is 1. And what is delta at 1? The unit sample has a value only at n equal to 0, right? For the rest, the value of delta would be 0. So this is going to be 0. Okay, this is 0 by the definition of delta. So when you add them up, you're going to get A. Right? Now when n is equal to 2, you have y at 2 equal to A times y at 1 plus delta at 2, right? And delta at 2 is again equal to 0, and y at 1 is 1 from the previous sample. So when you add them up, you're going to get a squared. And if you do this, if you continue doing this, okay, you're going to find that for an arbitrary n, the output would be a to the n. Okay, a to the n, right? You can use a mathematical induction to prove this, but I'm not going to do that. You can conclude that y at n is equal to a to the n, but this is not enough because we know that at negative values of n, y would be 0, right? So we need to multiply this by un, okay, to make sure that you won't get any y when n is negative. So multiplied by un here. And because this is the output when the input is the impulse signal with no initial conditions, so we know that this signal is actually the impulse response. So we can conclude that the impulse response of this system is a to the n un. All right. So you see, it's not that difficult, right? It's not that difficult. And if you plot the graph, of this, assuming that a is less than 0, assuming that a is less than 0, I'm sorry, assuming that a is between 0 and 1, the graph of h would look like this. Uh, oh, 1, right? 1 a squared, a cubed, a to the fourth, oh, and so on. And when n is negative, h would become 0. Here, minus 1, minus 2, 1, 2, 3, 4. This is h. This is 1, I'm sorry, 1, a squared, a cubed, a to the fourth, and so on. So this is how this impulse response is plotted. Remember, I'm assuming that A is between 0 and 1. If A is greater than 1, if A is greater than 1, then the exponential will be growing. But now A is less than 1, so we have a decay exponential. If A is negative, but if A is negative, if A is negative, then the graph will be like this. It will be go back and forth between positive and negative values. If A is negative, you see that? If A is negative, then H will be positive when N is an even number, and H will be negative when N is an odd number. But here A is positive, so H will always be positive. Okay. Now let's do another example. Uh, uh, let a discrete time LTI system with as the impulse response h of n equal to a to the nun, okay, where a is between 0 and 1, right? Find, we want to find the zero state response when the input is the unit step signal. Okay. So what is going on here? All right. What is going on is we have a discrete time LTI system, right, where the impulse response is given as a to the n un. Okay. Actually, this impulse response is this system is just the system in the previous example. If you notice, right, I'm using the result from the previous example in this example, right? Now, we're given the input of un to this system, right? And the goal is to find the zero state response yn that results from this input from the system. Now, to find this, we know that the zero state means zero initial conditions. The zero state response can be determined using the convolution sum. Okay, the convolution sum between xn and hn. Okay, so y, which is what we are after, is equal to xn star hn. Okay, and the way that the convolution sum is defined is summation going from negative infinity to infinity, x of k, h of n minus k. Now, the next step, now this is the definition, all right? This is a general definition, but now to apply the conditions given in this example, we have to apply the the function x here in the summation as well as the function h in the summation. Now, this example states that the input x is the unit step, right? So we need to plug in u into x. But in this summation, the variable inside the brackets is k. So we need to change from n to k, right? So we have to have summation going from minus infinity to infinity u of k. Okay, u of k. And then h is a to the nun, right? So when we plug it in, this is h of n. This is h of n. So, but we have to plug in, instead of n, we have to plug in n minus k, right? So n minus k will go to the exponent of a as as well as we go, as well as into the bracket of u, right? So we have a to the n minus k, u at n minus k. Okay? Now, we need to think about this, right? The first thing that we should look at is UK. Now, UK, we know the value of UK, right? UK is 1 whenever k goes from 0. But if k is negative, UK would be 0. So the summation here has to go from 0, right? Otherwise, UK would be 0. So it is useless to go from minus infinity. So I have to change the lower bound of the summation to be 0 to infinity. Now, whenever k is in this range, u will be 1, right? So I don't need to write down u anymore. Okay, so I'm just going to skip to a to the n minus k, u of n minus k. Now, the second thing that we need to look at is this term, which is u of n minus k. Now, you remember the value inside of the brackets have to be positive or 0, right? But here we have n minus k and c. N minus k is positive when k is not greater than n. Okay, if k is greater than n, then n minus k will be negative and u will be 0. So the index of the summation will have to go as far as k equal to n. Because if k is greater than n, then u would be 0. Right? So I have to change from infinity to n. And when I do that, I can get rid of u because u would be equal to 1. So let's do that. So I have k going from 0 to n, and a of n minus k, right? But when I do this, I have to take a note here that when I write this down, n has to be greater than or equal to 0. Okay, because if n is negative, then this cannot be true, right? Regardless. So I have to make a note that n has to be greater than or equal to 0. Here you see the index n here cannot be negative, right? Because k goes from 0. Now, from this point on, right, you have to know geometric sum because it is really a geometric sum. You have to be able to evaluate geometric sums. So the index of the summation is k, right? So n is a constant. So I can pull n out, right? So I have a to the n. I can take it out from the summation that at the inside of the parentheses would be going from 0 to n, right? And I have a inverse because actually it is a to the minus 1, which is called a inverse to the k, right? Okay. Now, I'd like to like for you to recall geometric sum. Okay. Geometric sum says that if I have 1 plus r squared plus r cubed plus blah 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 plus r to the n. Okay, if I add them all, n plus one term, I'm gonna have 1 minus r to the n plus first over 1 minus r. Okay, also if I have 1 plus r to the second plus r cubed, now we have infinite number of terms added. The result would be 1 over 1 minus r as long as the absolute value of r is not greater than 1. Now, these are the geometric sums that I think you have to know. Okay, so be sure to write this down. Oh, sorry. Be sure to write this down in your notes before you go into the exam, because I'm not gonna give you this, right? If you don't think you can remember this, which I think you should. If you don't think that you can remember it, you have to write it down. Okay. Now, when we know this is just r to the zero, right? R to the zero, and you see, we are interested in this form of the sum, right? Because we are adding them finite terms, finite number of terms. So, but here r is this is r, right? This r is equal to a inverse, right? So we have to plug in r equal to a inverse on the right hand side of the geometric sum. So we have, from the geometric sum, we have a to the n times 1 minus a inverse, okay, to the n plus 1 over 1 minus a inverse. Okay, and the rest is just algebra, right? The rest is just algebra, and you can bring. So well, actually, I have a to the n minus a to the n times a to the minus n times a to the minus 1, right? Divided by uh, what? A minus 1, and then multiplied by a, right? It's just simple algebra, straightforward. You don't have to worry about it. So a to the n times a to the minus n will cancel and will give you 1. So I have uh, a to the n plus 1 minus 1 over a minus 1. Okay. And usually a is less than 1, so I think I should switch him here. But we have to take into account that n has to be greater than 0, right? So the answer would have to be this and multiplied by un. Okay. So the zero state response from the system is 1 minus a to the n plus 1 over 1 minus a and times un. Okay, the reason why un is present is because the output starts from n equal to 0. When n is less than 0, the output would be 0 because the input is not there yet and there are no initial conditions, so you know, the output would be 0. All right. Now, if you want to plot this graph, you will find that the graph of y, the zero set response uh, for the unit impulse, I'm sorry, unit step is this. Zero. Something is not correct, is it? N plus A plus 1. Let me go back a little, see if something, see whether something's wrong. Um, Here, A to the N minus 0. 1, 1. Oh, okay, right. No, it has to be this. Is it? Okay, let's see. Ah, sorry. It's this. Yeah. Okay, 1, and then it goes up, and it will reach steady state as n approaches infinity. And the value of the steady state is 1 over 1 minus a. Here, this is the steady state is 1 over 1 minus a. This is the zero state response. All right. Any question, please? No? Okay. Let's do another one. Uh, Now I'm gonna write down h. Okay, let hn be let's say be a to the n un again. All right, and xn be b to the n un. Okay, we want to find the zero state response by n from this system. So why don't you uh, think about it? I'm gonna give you 1 minute, a couple of minutes, a few minutes to think about it, how to find the zero state response. I can start it for you. Y is summation, right? Convolution sum that goes from negative infinity to infinity. You can begin with x or h, doesn't matter. The result will be the same. Okay, in this case, I'm gonna start with x. Okay, and go from here. This is the starting point, and then we go from here. So next step is to plug in x and h, right? Use those uh, functions given and calculate. But the I think the tricky step is to evaluate the summation. That's the trickiest one. So what do you say? Not so hard, actually. Times it. Wait. Okay, so I'm gonna go ahead, and if you're not done yet, you can continue working on yours, and we're gonna verify our results together to see which one is correct. Because personally, I'm not sure whether mine's correct. So let's plug him in. All right. If you don't know how to do it, you can look at me. But if you are doing your work, you don't have to look up. So I have xk equal to b to the k uk, and h n minus k is a to the n minus k u of n minus k. So using the same thoughts as we did last example, I can start from k equal to 0 up to n, right? And when I do this, all the u's are gone. And I'm going to have b to the k, a to the n minus k, right? And then I have to take a note that n has to be at least 0, otherwise it wouldn't work. And then I can take a to the n out of the summation, and I have this uh, b over a, right, to the k. Okay, and the rest is just a repeat of the previous one, right? And then I have, this is a geometric sum again. So I'm gonna have a to the n, 1 minus b over a to the n plus 1 over 1 minus b over a, right? And the rest is just algebra. Okay, so I'm gonna leave it here. Right? I trust that you all can do this. Right? So blah blah blah. Right? But you have to be sure that you multiply it by un. Okay. Don't miss this one. Okay, don't miss this one because it's completely different if you don't have this term. Okay, all right. Any question? Now let's do one more. Oh, two more. This time, Hn, the impulse response, is Un. Okay, and the input is also Un. So what would be the zero state response? You all can do this, right? I'm not gonna give you the details. I'm not gonna do the details. You can go from there and rearrange the terms, make it nicer. So in this example, the zero state response is so now I'm gonna cut to the I'm gonna leave all the unnecessary details there, and I'm gonna cut to the point. Minus infinity to infinity. Now u of k, right? And then u of n minus k. Okay, and then we know that we have to change the boundaries of the summation to go from 0 to n. And then once we do that, all of the u will be 1. Okay, and then I have to mark that n cannot be negative. Now, so this, what does it mean? It means that you have to add 1 n plus 1 times, right? How many times you have to add 1? How many ones are there in summation? N plus 1 number of ones, right? So this is just when k is 1, I'm sorry, when this term is when k is 0, right? When k is 1, when k is 2, until when k is n. Okay, so there are n plus 1 terms. And you know that if you add them up n plus 1 times, you're gonna get n plus 1. And then don't forget un. Okay, so this is when u is convolved with u. Last example. This time, okay, I'm gonna say h, the same one, a to the n u n. Now go back to a to the n u n, and now xn is 3un minus b, I'm sorry, minus 2 times b to the n un. Oh, sorry. The screen is probably too big. So how do we go about doing this? Of course, we're not going to use the direct method, right? But we're going to use one of the properties of convolution sums. And that would be distributive property, right? You know, here's how it goes. Yn, okay, is equal to, let's do this, h of n, right? And then convolve with x, okay? As I told you earlier, it doesn't matter which one to begin, all right? I can begin with h or I can begin with x, doesn't matter. Here I start with x, h, sorry, h, not x, h. So, but then I plug in h as a to the nun, right? And then I convolve it with 3un, which is x, minus 2b to the nun, right? And then I can use the distributive property of convolution sum to bring this inside the brackets, okay, inside the brackets. Now, from distributive property of the of the convolution sum, I have 3 times a to the n un, okay, and convolved with un. This is the first term, and the other term minus 2 a to the n un convolved with b to the n un. Okay, and what do we know about each term? We know the first term, right? The left term from the first example. And we know the right term from the second example. We did this already. So we're going to use those results in this. In the first example, I'm just going to copy it here. This is the left term, right? We did this already. So I'm just going to copy it. Okay. I'm not sure if you recall. Yeah, so this is the first term, but I have to remember to put 3 at front, right? Because we have 3. Now, as for the second term, I think I did this already, but it was right here. This is the second term. Okay, and then I'm just gonna copy it. Okay, copy it and put it here. But don't forget the minus 2. All right. And then I think you can do the rest. Okay, so I'm gonna leave it open and ask you to do the rest for me. So this is how the distributive property can be applied, right? It's very useful. In other words, actually you can break the input or the impulse response into smaller terms, and you do the smaller terms, then you add them up later. Okay. All right, any question, please? Oh, actually, the first one. Yeah, sorry. This is correct. This is correct. Sorry. Okay. No questions? Now, the next topic is called the unit step responses. Now, this is the special condition where the input is the unit step signal. Okay, when the input is the unit step signal, then the zero state response becomes u of n, right? Convolved with h of n. Okay, and then you have summation k goes from 0 to well, I shouldn't skip it, minus infinity to infinity u of k h of n minus k. Okay, and this is just summation that goes from 0 to infinity. All right, we know this because u starts from k has to start from 0, right? Otherwise u would be 0, and then u is 1, so I don't have to worry about u, and then I have h at n minus k. Now, I'm not happy about this n minus k here. I want to make it simpler. Okay, to make it simpler, I have to think about what this summation really is. So let's unfold this summation. If we unfold this summation, I'm going to use orange ink. When k is 0, I have h of n, right? When k is 1, I have h of n minus 1, right? When k is 2, I have h of n minus 2. When k is 3, I have h of n minus 3. And this goes on forever, doesn't stop, because k goes to infinity. But then, if you look at this sum, it says that I can actually write this sum as k going from minus infinity to n of h minus k, h, hk, right? So if you look at this sum, it is actually going from, the index goes from minus infinity to n, h of k, right? Look at this and convince yourself that they are the same. Do you see? Do you see that they are the same? Here. This goes on until the variable, the index inside the brackets are minus infinity, right? So here, minus infinity up until n, right? Up until n. So this summation and this summation are equivalent, completely equivalent. So we know that using the result, the unit step response from a discrete time LTI system is given by let's use the notation S to stand for unit step response, equal to summation k going from minus infinity to n h of k. All right. So this is a shortcut formula to find the unit step response. For example, let if h k h n is equal to un, if the impulse response is un, then if we apply the unit step signal into this system, we're going to have the unit step response, of course, zero state, right? Equal to summation going from minus infinity to n, and then hk is going to be uk, right? But uk starts from k equal to 0, so this is summation going from 0 to n and 1, and we have n plus 1 un, which is in consistence with what we found in the previous example. Okay, so this is a kind of like a shortcut formula when you know that the input is the unit step signal. Okay, now I'm going to call this equation 1, okay, for reference. Now, oh, sorry. Now, from equation 1, okay, let's unfold again. Let's do this trick again. I'm going to unfold the summation in equation 1. When I unfold it, I have Sn equal to Hn, okay, plus h of n minus 1 plus h of n minus 2 plus h of n minus 3, and so on, right? Now, uh, let us plug in, instead of n, I'm going to plug in n minus 1 inside the brackets, okay? Here, I go from n here to n minus 1. Okay, I go from n to n minus 1. When I do this, the first term has to be h of n minus 1, right? h of n minus 1. So I have h of n minus 1 plus h of n minus 2 plus h of n minus 3 and so on. And then I can subtract these two equations. Now if I subtract these two equations, all of this will be gone, right? All of this will cancel out, leaving me only this term, right? So the right hand side would be h of n. Okay, the right hand side would be h of n. Now the left hand side will be s of n minus s of n minus 1. And now I have another formula. Okay, if we know this formula, this equation tells us that if we know the new step response, then we can find the impulse response. Okay, so we have the impulse response can be found from the unit step response by subtracting these two terms together here. Okay, the unit step it's actually the impulse response can be found from the unit step response. And vice versa. Okay. For example, in the previous example, in the last example, we had s of n equal to n plus 1 un, right? This is from the last example. The unit step response was n plus 1 un. Now I'm going to try to find the impulse response knowing the step response here. Then h of n equal to s of n minus s of n minus 1. Okay. Now I can plug in s of n as n plus 1 un. Okay. And s of n minus 1 as n minus 1 plus 1 u of n minus 1. Okay. And then I have nun, right? Plus un minus nu of n minus 1. So what is this then? What do you think? It is actually n times un, right? I pull n out. I group the first and the last terms together. So I have n, and inside parentheses are un minus 1. Okay, and then I add un in the back. And so tell me here, what is this equal to? Un minus 1. What is this equal to? What is this? Can you tell me what this is? This is just delta n, right? This is delta n. Can you see that? Can you see why this is delta n? Because un is 1, is all 1 when n starts from 0, and un minus 1 is all 1 when n starts from 1, right? So if you subtract them together, you're going to have 1 minus 0 at only n equal to 0. The rest is just 1 minus 1. So the rest will be gone. So you have just one value left, and that is at n equal to 0. That is by definition delta n. So you have uh, n delta n, right, plus un. But delta n has a value only when n equal to 0, right? When n equal to 0, delta is 1. But when n equal to 0, this term is 0. So if you multiply them, you're going to get 0, right? And delta n is always 0, regardless of the value of n. If n is 0, then this term is 0. But if n is not 0, then delta is 0. So regardless, you're going to have this one equal to 0 anyway. So this one is gone, right? Can you see it? This one is always 0. Okay? So you're left with un. And this is consistent with the condition given in the last example, right? So they agree, okay? The results agree. Okay. Any question, please? Okay. Now, it turns out that some of the properties of systems, okay, can be determined by looking at the impulse response. If the system is linear time invariant, just as in chapter 2, right? Now, it turns out that some of the properties of discrete time LTI systems can be determined using only their impulse responses. Okay, those properties are first memoryless properties. You can you can you can determine whether an LTI system is memoryless by looking at the impulse response. That is, an, a discrete time LTI system is memoryless if and only if the impulse response is a multiple of the unit sample. So this notation, if and only if, you know what it means? It means necessary and sufficient condition. So memoryless property is equivalent to the impulse response being a multiple of the sample signal, sample function. In other words, if this equation is not true, then the system is not memoryless. On the other hand, if the system is memoryless, then this equation is true. So that is what if and only if means. The second property is the causality property. A discrete time LTI system is causal. Do you remember what a causal is? A causal means that the present output doesn't depend on the future input. I'm not sure if you recall it. Okay. Again, a causal system means that the present output does not depend on the future input. It can depend on the present input. It can depend on the past input, but not future input. So this is what a causal means. Discrete time LTI system is causal if and only if the impulse response is zero whenever n is greater than zero. Okay, so no, sorry, less than zero. I got it the other way around. So a causal system has the impulse response starting from zero only. It cannot start at time prior to zero. It has to start at least at time zero. Okay? Then the third, no, that was the second one, right? The third property that can be easily determined if the system's LTI is bibostable. If you recall, the bibostability is the trickiest one to determine, right? Because you have to assume first that the input is bounded, and once the input is bounded, then you have to prove that a particular system has the bounded output. Okay, that is what bibostability means. But you don't have to do all those because all those are pretty involving. It is hard to do. But when the system is LTI, you can skip those process by just looking at the impulse response. Okay, uh, discrete time LTI system is bounded input, bounded output stable if and only if we call it Hn is absolutely summable. Okay, absolutely summable means that if you take the absolute value of Hn, okay, if Hn is negative, you have to make it positive. That is what it means. Take only the magnitude value of H and you add them up, all samples. You add the absolute value of Hn for every sample. The result would have to be finite. Okay, if the result is infinite, if the result is not finite, then the system is not stable. But if the result from this summation is finite, then the system is stable. Now, this deserves some example. For example, let us have a system where the impulse response is point, let's say, negative 0.6. Negative 0.6? Yeah, negative 0.6 to the nth un. Okay? Is this system memoryless? The first question, is it memoryless? No, it is not, right? Because it is not delta, right? The system is memoryless if it is multiples of delta, but this is not delta. This is u. This is something, not delta. So this is not memoryless, obviously. Not memoryless. So it has memory. In other words, it has the word it has memory means if you want to determine the present value of the output, then you have to use some of the past values of the output. So this is what memoryless means. Is it causal? It is causal. Now, why? How do I know it's causal? Because of the u here. The presence of the u here tells us that Hn starts from zero, right? Hn doesn't start from negative values of n. So because Hn starts from zero, this condition here is satisfied. Okay, so it is causal. Causal. Now, is it stable? To check whether this system is stable, I have to check this summation, right? To see whether it is finite or not. So let's do that. for stability, okay, we have to check the summation. N goes from minus infinity to infinity, absolute value of minus 0.6 to the n un, right? Okay, um, and because of the term un, right? I know that I can start from 0, right? So this is equal to summation that goes from 0 to infinity, minus zero point 0.6 to the n absolute value. Okay, and I know that the terms inside of the absolute symbols contain both positive and negative values. Right? So if you add them up, it's rather tricky to take these absolute values, absolute symbols out. But we don't have to find the value of the summation. We only have to determine whether it is bounded above or not. Okay? We don't, the thing is we don't need to find the value. We don't need to evaluate the value. We have to just know that if it's bounded or not. So you see, this summation, if you look carefully, it is going to be less than or equal to summation when n goes from 0 to infinity, and then 0.6 to the n. Can you see that? If you are not convinced that this is true, then you might have to think about this. What is this? If I have 0.6 minus 0.2 plus 0.5 minus 0.1, okay, this is less than or equal to 0.6 plus 0.2 plus 0.5 plus 0.1, right? Are you convinced now? This is called a triangle inequality, okay, in real analysis here. Absolute A plus B is less than or equal to absolute A plus absolute B, right? Actually, I have to put in the absolute value here, okay? But then, you know, I don't have to put the absolute symbols here because I know that 0.6 to the end is always positive, right? So I can drop the absolute symbols to get that. Okay, and then I have this summation is equal to 1 over 1 minus 0.6, and that is yeah, 0.6, 1 over 0.4, and that is 2.5. Okay, is this finite? Yes, it is, because I know that this summation is less than or equal to 0.5, so it is finite, and because it is finite, it is stable. So since this summation is finite, system stable. Okay. In fact, oh, what about this? Uh, if I have Hn equal to 0.1 to the nun plus 0.2 to the nun, can you determine whether this system is stable or not? this is of course causal and memoryless, right? So I don't have to think about it. So the question remains whether it is stable or not. So to check stability, I simply need to check this sum, right? And again, I'm going to use a triangular inequality to say this, right? Can you see? Are you convinced? This is from triangular inequality, okay? And the left term is using geometric sum, right? So it is 1 over 1 minus zero point 0.1. And the right term is 1 over 1 minus zero point 0.2. So you see it is finite, right? Both of them are finite. The first one is, I think, it is 1.11 something. Okay, then the second one is 1.25. And if you add them up, you see that the result is definitely finite. So this system is stable. Okay. In fact, you may find this geometric sum useful. Okay, if you add 1 plus r to the second plus r to the third plus r to the fourth, blah blah blah, the result is finite if and only if um, the magnitude of r is less than 1. Okay, you may find this one useful. This is from mathematics, right? This is from math. The geometric sums finite if and only if the magnitude of r is less than 1. If the magnitude of r is equal to 1, it is not finite anymore. Okay, and if it's greater than 1, it's obviously not finite. Okay, it's because you have a divergence. All right, so that's it for times out, and we're exactly at 12, almost 15. So we should be done. So any questions, please, about this? Now, I'd like to spend the last few minutes of our time talking about the exam, the final exam. Again, the final exam is next Wednesday, right? Next Wednesday. The room is the same as when you did midterm, but it's 201, which is 2 floors down this way in this wing. Uh, you can bring in a sheet, A4 sheet, both sides written. Don't forget it, right? Last time you forgot it. You can bring in a simple calculator, a pretty silly calculator that, you know, the content of the exam will be from Fourier transforms until this, up to this. Um, I have put together practice questions about Fourier transforms, and I've already posted it on Google Classroom, so please check it out. Um, you you definitely have to write down properties of Fourier transforms, as well as some important Fourier transforms on your A4 note. You have plenty of space to write them down, so please don't forget. It is your responsibility to write them down. Uh, You may have to do integrations. Okay, no, you definitely have to do integration in the exam, but don't expect fancy integration, right? Just a simple integration. Yeah, you have to do this. You have to be able to. You have to be able to find this integration. Well, if you don't know, if you don't know, it is x to the n plus 1 over n plus 1. Okay? Right. There will be complex numbers in the exam, but yeah, so you have to be able to to work on complex numbers. Anything else? You will need to draw graphs in the exam. So you know, work on the graph. You have to prepare for it. Um, there are 5 questions in the exam. The total score is 30. Okay, 30 as we have discussed already. Um, in each of the questions, in each of the 5 questions, there may be sub questions. Okay, sub questions. My advice to you is I strongly advise you to work on the practice problems, especially in Fourier transforms. You may find it useful, right? So look at it. Look at it. If you don't look at it before going to the exam, you may find the exam, some of the exams, pretty hard. Okay, but if you've already looked at it, you may find some of the questions easy. Okay, so please look at it. Anything else? No. Any questions, please, about anything? Again, for discrete time signals and systems, there is another tool that I haven't taught yet, and that is the Z transforms. Z transforms just like the concept of Z transforms, just like the Laplace transform. Laplace transforms applied when the time is continuous, but Z transform is applied when the time is discrete. So the concept is just the same, but you have to change from integration to summation. That is Z transforms. Okay, so concepts exactly the same. Partial fraction expansions exactly the same. Okay, so if you understand what is going on, if you can use the Laplace transforms, I think you definitely can use Z transforms. You have to adjust a little thing, minute thing, okay, from integration to summation. That's the Z transform. Unfortunately, we won't be able to cover it in time. So I guess that's it. Any questions, please? Okay, if there are no questions, I'm gonna